Grignards and alkylithiums both consist of an alkyl group complex to a metal. A Grignard reagent is an alkyl group complex to a magnesium and a halogen, typically MgBr. The magnesium has a +2 charge, the halogen has a -1. To get charges to balance, the alkyl group has to be R-. Alkylithiums are similar. Lithium is a +1, so the alkyl group has to be an R-. These alkyl groups are very good nucleophiles and very good bases, as we talked about in lab. So you have to make sure when you're using Grignards that there is no water around. They can attack the carbonyl carbon of aldehydes and ketones to give alcohols. Remember, we saw in lab that a carbonyl has a resonance structure where the carbonyl carbon has a delta plus. So the Grignard reagent, R-, likes to attack that delta plus. So it attacks right at the carbonyl carbon right there. That's pretty good for synthesis because when I do the mechanism, I can create all kinds of alcohols that vary just depending on my choice of ketone or aldehyde. So the product from this generic reaction after I acidify would be the Grignard attached to the carbonyl carbon, and then the oxygen becomes an OH, and I've made an alcohol. The reaction of a Grignard or an alkylithium with a ketone right here gives us a tertiary alcohol. You can see that by just looking at the mechanism. So let's go ahead and let's redraw the Grignard. I'm going to ignore the MgBr part and just put minus charge there. It attacks the carbonyl carbon, electrons pushed up onto the oxygen, and my intermediate is going to look like this. There's an O-. Then when I add H3O+, I protonate that, and I have created a tertiary alcohol. Likewise, if I use an aldehyde, what I'm doing is I'm eliminating that second R group right there and replacing it with an H. What that means is that instead of a tertiary alcohol, I'm missing an alkyl group, and I'll be making a secondary alcohol. So let's go ahead and take a look at how that works. We'll redraw our alkylithium this time. Same mechanism, it attacks the carbonyl, electrons are pushed up, and I'm going to have an O- for starters. There's the hydrogen because it's an aldehyde. I've attached that isopropyl group. And then when I protonate, add H+, I end up forming an alcohol. And instead of having 3 alkyl groups, it only has 2, and so it's a secondary alcohol. Finally, if I want to make a primary alcohol, I'm kind of limited in my choices. My aldehyde cannot have any R groups on it, so I'm stuck using formaldehyde, which contains no extra R groups. So what that's going to do, if you take a look at the mechanism, let's have the Grignard attack right there. Electrons go up. I will have a C, 2 H's, and an O-. And then when I protonate, there's my Grignard part, and I have C, OH, H2. I've got a primary alcohol, and I have just added 1 carbon atom. So it makes it 1 carbon atom longer than the original Grignard or alkylithium. If I wanted to make it 2 carbon atoms longer, I can use a compound called ethylene oxide. It's a 3-membered ring with an oxygen in it. Ethylene oxide's pretty strained, and it's really easy to pop open when you hit it with a nucleophile. So a nucleophile attacks the carbon, and the ring pops open, pushing electrons on the oxygen. It's the more electronegative atom. And you end up with your nucleophile attached to a carbon, which is the carbon that is right there. So the nucleophile is attached there. That carbon is attached to the other carbon in the ring, and then dangling off the end is your O-. So, if we take the alkylithium, it attacks right there, electrons up on the oxygen. There's my alkylithium. Here's the carbon, and then O minus. And when I do H plus, I will end up with an alcohol. It's a primary alcohol, and what I've done is I have added 2 carbon atoms to the chain. So you have some options with a primary. You can add 1 atom or 2 atoms, depending on what you choose to use.